Welcome to Statistical Sampling 3, Intuition through Simulation. This module will consist of 3 tutorials. In Tutorial 3a, we'll look at the distribution of the sample mean, x bar. Tutorial 3b, which you may want to skip if you only care about sampling, is a technical note. It simply helps you understand how we generate the population in the background of the spreadsheets you will see in this tutorial. And then in Tutorial 3c, we will look at the sample standard deviation S and the population standard deviation sigma and develop some insights there. But for now, let's assume that the population distribution we were interested in looked something like this. Perhaps this distribution represents the amount of beer a somewhat rude and perhaps somewhat drunk bartender pours into his customers' glasses. He pours a lot into the glasses of customers he likes, and all other customers he pours usually quite stingy drinks, but since he's drunk there's quite some variability across the drinks he pours. While this may not be a very realistic distribution you encounter in practice, it will serve us well to develop some intuition about sampling in general, and, quite frankly, to develop that intuition under rather adverse circumstances. Of course, in general, when we do sampling, we have no idea about the underlying population distribution. Instead, we want to learn something about it. In particular, what we usually want to learn is what is the average in the distribution. So in this case, what is the average drink size? And what's the variability in that distribution? In our case, what is the standard deviation of the drinks poured? But here, to develop insights, we take the opposite route. We assume we know the population distribution, and from that, we will develop some insights about the sample mean and the sample standard deviation. To do this, I have entered this distribution into Crystal Ball and let Crystal Ball simulate 36 observations from that distribution. So let's see how this works. If I press Step, Crystal Ball will randomly take 36 observations from this distribution. So for example, observation 1 is 142.57 milliliters. Observation 2, 134.08 milliliters. And so on up to observation 36, which is 284.28 milliliters. On average, each glass contains 186.6 milliliters, and the standard deviation within the 36 observations we had is 93.97 milliliters. For now, we will ignore the standard deviation. We will return to the standard deviation in video tutorial 3c. Let's focus on the average. Our average of 186.6 is the result of 36 random numbers. Just by chance that we chose or that we observed those 36 numbers. We could have observed 36 completely different numbers. And if we had taken a different sample, we would have. So let's see what happens. That's the beauty of Crystal Ball. We can just create another sample and see what that sample yields. Oh, this sample would have yielded an average of 200 and 0.02 milliliters and a standard deviation of 112.08. Yet another sample might have yielded an average of 193.66, and yet another sample an average of 173.12. Now, in practice, we would have taken one sample, one of those 4 perhaps, and more importantly in practice, we would have no idea about the underlying population distribution. So we would have no idea how good our estimate was. Right now we have an average of 173. That's not particularly good, given that one of the other samples had an average of 200, which was almost right on the dot. So, since the average in a sample is a random variable, it must have a distribution. What would that distribution look like? Now here's the beauty of crystal ball. We can just pretend we take 1,000,000 samples of size 36 each and then see what overall the average does. So let's do exactly that and see what happens to the sample mean. Look what arises slowly if the trials get larger and larger out of the ashes. The sample mean starts to behave more and more like a normal distribution, and eventually, at 1,000,000 trials, the mean is exactly or almost exactly at 200, it's at 199.99, and the standard deviation, interestingly, is at about 16.65. But look at the beautiful distribution of the mean. So let's think about what this means. Well, it looks like, in average, a sample hits the mean right on the head. So in average, when we sample, we can be assured, it looks like, and we will later prove that in tutorial 3C, it looks like that in average we get the mean exactly right. However, there are also some really bad samples. For example, about 2.5% of all samples would give a mean of 168 milliliters or less. And similarly, about 2.5% of all samples would yield a mean of 232 milliliters or more. 5% of all samples will have a mean of 174 or less, or 228 or more. The unfortunate thing, of course, will be that if we take a sample, we have no idea if we are here, or if we are somewhere really close to the mean. That means essentially that just saying, well, our best shot, let's suppose we are here, our best shot of calling the mean 232 milliliters is not sufficient. We need to give an interval and a level of confidence, how close we think we might be to the mean. This is what we will do in tutorial 4. For now, we have established two things. It looks like the sample mean follows a normal distribution, and it also looks like that the expected value of the sample mean is identical to the mean of the population distribution. But what about the standard deviation of the sample mean? Does this relate in any form to the standard deviation of the population? Recall that the standard deviation of the population was 100. The standard deviation of the sample mean in this example is only 16.65. So roughly a sixth, or almost exactly a sixth, of the standard deviation of the population. A sixth? Our sample size was 36. 6 is exactly the square root of 36. Now, did we find a third pattern here? Let's recap the three things we found. First, we found that the sample mean is very, very close, if not identical, to the mean of the population mu. The population mean mu was 200, the mean of the sample of all those 1 million samples, was 199.99, so almost identical. Second, we found that the sample mean follows a normal, or seems at least to follow a normal distribution. And third, we found that the standard deviation of the population was 100, whereas the standard deviation of the sample mean was only 16.65, almost exactly 1/6, or the square root of 36, of the population standard deviation. The question, of course, is, does this pattern hold for other distributions as well? So let's try this first with the same distribution, but with a different sample size. Let's say sample size n equals 30. So here I have set up the same population distribution in crystal ball, but now with a sample size of n equals 30. So let's see what happens. Let's again step into the simulation. Again, we get now 30 observations for each time we step through the simulation. And now let's run through it and see what happens to our average. As you can see, the sample mean seems to quickly again assume a normal distribution. Again, the sample mean seems to be close to 200, but now the standard deviation is a bit larger and seems to be a bit over 18. For 1 million trials, the distribution eventually looks like this. Again, the distribution of the sample mean looks like a beautiful normal distribution. But let's compare the mean and the standard deviation directly against the underlying population distribution. Again, the mean is almost perfect. The standard deviation, recall, was 100 for our population. It is 18.27, or 18.26 rather, for the sample mean. The ratio is once again exactly the square root of n, the square root of 30, which is 5.477. So once again we have this phenomenon that the standard deviation of the sample mean is equal to the standard deviation of the population divided by the square root of the sample size, in our case 100 divided by the square root of 30, or 100 divided by 5.48, which is 18.26. Okay, let's try the whole thing with a different distribution. Let's see if it there holds too. This time I use the exponential distribution that looks like this. A peculiarity about the exponential distribution is that its mean and its standard deviation are identical. In this case, we have an exponential distribution with mean equals 100 and a standard deviation of 100 as well. I have set this up in a straightforward way in crystal ball, and again, let's see what happens if we run 1 million samples of size 36. This starts to look like a normal distribution again, and eventually, for 1 million samples of size 36, it will look something like that. However, let's have a closer look. It's not exactly a normal distribution. The tail on the right-hand side is just a bit fatter than the tail on the left-hand side. In regards to the other two criteria, however, the mean is once again right on the money. We have 99.99 as an estimate for a mean of 100, and the standard deviation of the sample mean is again almost exactly equal to the standard deviation of the population divided by the square root of the sample size. In this case, the standard deviation of the sample mean is 16.69, which is very close to 100 divided by 6, the population standard deviation over the square root of the sample size n equals 36. There are 4 things that you should take away from this tutorial. The first thing, as obvious as it may sound, is oftentimes overlooked. The sample mean x bar is a random variable. That means that each time we take a sample, we will get a different value for the sample mean. Since it is a random variable, it must have an expected value, a mean. And this expected value is equal to the mean of the population distribution mu. It also must have a standard deviation. That standard deviation, sigma x bar, is equal to sigma divided by the square root of n, the standard deviation of the population divided by the square root of the sample size. And finally, it looks like the sample mean distribution is a normal distribution, at least usually, with parameters mu and sigma over the square root of n. In a later tutorial, we will see the crucial role the sample size plays in the last observation. In tutorial 3b, which is just a technical note, you will see how I generated the population distribution with crystal ball. You can easily skip this and don't lose any insights about sampling. 3c is more exciting though. There, we look at the sample standard deviation S and the population standard deviation sigma and how they relate. Thus, we will introduce a third standard deviation. So far, we looked at the standard deviation of the population sigma, and we looked at the standard deviation of the sample mean sigma sub x bar. In 3c, we will look at the sample standard deviation S. I will see you then.